Welcome. So, in the last lecture, we have discussed about various uninformed search techniques. That is we discussed about informed search technique, that is the heuristic search algorithms. So, in this lecture, basically, we'll be discussing on the importance of heuristic function. So, so the heuristic function actually plays an important role in effectively solving the problem. So how effectively the problem will be get solved, that actually depends on the heuristic function, how nicely the heuristic function is designed. The more good the heuristic function is, then the problem will be more effective. Okay, so we'll be discussing that with an example. So the quality of an heuristic search algorithm depends on its heuristic function. So that is the point. The quality of a heuristic search algorithm depends on the heuristic function. So already we have discussed that there should be uh, for an for an algorithm to be optimal, it should satisfy two conditions. That is, the heuristic function should be admissible and also consistent. But again, for example, sometimes you may have two heuristic functions to solve a problem. Let us say as h1 and h2. H1 is one heuristic function, h2 is another heuristic function. Let us assume that both h1 and h2 were admissible and consistent. Then also one of the heuristic may be better than the other heuristic. So that's what we are going to discuss. Okay. So let us so we'll be discussing this based on the 8 puzzle problem. So let us consider an 8 puzzle problem. So in a 8 puzzle problem, you will be given an initial state, and there will be some goal state, and the tile should be moved to the adjacent empty location accordingly to reach the goal state. So here the heuristic function can be framed in two ways. So we are discussing two methods of framing the heuristic function. One is called as h1. H1, it represents the misplaced tiles. How many tiles are misplaced when compared with the goal state? So that is called as h1. Whereas h2 is sum of the Manhattan distance of all tiles to the goal position. That is, for each tile, you have to compare with the goal position of that particular tile, how much it is distant from the goal state. And then you have to sum up all the, like that you have to calculate for all tiles and you have to sum it up. So that is called as H2. So these are two different heuristics. The problem can be solved either by using H1 or by using H2. So out of these two, which one is a better heuristic? That's what we are trying to understand. Okay. So let us discuss an example so that it will be clear. So see here, yeah. So this is the 8 puzzle problem. So this is an example for an 8 puzzle problem we are discussing. So so if you want to solve this problem using heuristic search technique, then we should have a heuristic function. So this problem can be solved by using any heuristic function, but we have to first frame the heuristic function satisfying that condition. That is, the heuristic function should be admissible, it should be consistent, all those things. So here we have two options. Either we can go with this heuristic function or with this heuristic function. What is this heuristic function? What it says, h of n is equal to number of misplaced tiles. That is, this heuristic function, what it says in the sense, how many tiles were misplaced. So that is our heuristic. So this is the initial state. This is the initial state and this is the goal state. So if you apply the first heuristic function, then what value here will be getting? So we have to check each of the slides from, you have to compare each slide from the initial state with the goal state, whether it is misplaced or not. Is 5 is misplaced? Yes, 5 is misplaced. 5 is supposed to be here, but in the initial state it is here. So it is misplaced. So one tile is so fifth tile is misplaced. So 1. Then you check whether 8 is misplaced. Yes, 8 is also misplaced. It is supposed to be here. It is, whereas it is in some other position. Is 4 is misplaced? No, 4 is not misplaced. It is in its correct position. Is 2 is misplaced? Yes, 2 is supposed to be here, but it is here. So it is misplaced. Is 1 is misplaced? Yes, 1 is supposed to be here, but it is here. So, okay. Is 7 is misplaced? No, 7 is not misplaced. It is in its correct position. Okay. Is 3 is misplaced? Yes, 3 is misplaced. Okay. Is 6 is misplaced? Yes, 6 is misplaced. So how many tiles totally misplaced? 1, 2, 3, 4, 5, 6. 6 tiles were misplaced and remaining 2 tiles were not misplaced. So in this case, the heuristic is what? 6. The heuristic value at this board position is 6. Again, if you change if you move this here, then the heuristic value will change. But this is how we calculate. If you use this first heuristic function to solve this problem, this is how we calculate the heuristic value. But this problem can also be solved using this heuristic function h2 of n. What it says means sum of distances of each tile to the goal. Sum of the distances of each tile to the goal. So this is the second heuristic. Sum of the distances of each tile to the goal. From each tile you have to see like how much distance it is away from the respective tile in the goal state. Okay. For each tile you have to check like how much distance it is away from the respective tile in the goal state. So this is actually different from this. Here in the first case we are only we are seeing like how many misplaced, that's all. We are not bothered about the position. Whereas in the second case we are bothered about where it is. Okay, so how much it is each tile at what is the distance when you compare, when you take this particular tile when you compare with the goal state, how much it was away from the respective position of that particular tile in the goal state. So you can say how much it is away in the sense, if you want to move to 5, then how we have to move. I mean, if this 5 should be moved to this location, then it can move either this way or it can move either this way. In either of this case, it has to make minimum how many moves? 1 and 2. So if it follows this way also, it has to make 1 and 2 move. If it follows this way also, it has to make 2 moves, 1 and 2, right? So then we can say that 5 is away from its actual position by 2 locations, right? Like this we have to calculate for every tile. Like this we have to calculate for every tile. So this is for 5. Similarly, we have to calculate for 8. 8, how much it is away from its location. So 8, if you see 1, 2, 3, either you can come this way or you can take this way. So if you take this way also, it is 1, 2, 3. If you take this way also, it is 1, 2, 3. So it is 3. Right. 4 it is in its correct position, so it is 0 plus 2. 2 it is away from its I mean its goal location just by 1 position. So just if 2 is moved there, it will be in its respective position. So it is just what? 1. It is 1. What about 3? 3 is supposed to be here. So it is 1, 2, 3. Or it can go this way also, 1, 2, 3. So it is 3. Sorry. So after 4 we will see 2. 2, then 1 we will see. 1 we will see. Okay. So 1 it is away from its position by 3 locations. 1, 2, 3 or 1, 2, 3. So it is 3. Okay. Then 7 it is in its correct location. So that is 0. Then 3, it is away by 3 locations, 1, 2, 3, or 1, 2, 3. Okay. 6, it is away by 1 location, so it is 1. So if you calculate this way, it is called, what is the heuristic value? 2 plus 3, 5, 5 plus 1, 6, 6 plus 3, 9, 9 plus 1, 10, 10 plus 3, 13. Okay. So this heuristic is also called as Manhattan distance. This heuristic is also called as Manhattan distance. Okay. So these are these are different. So for a given problem, you can have multiple heuristics. So that's what we are discussing. Out of multiple heuristic functions, one may be better than other. So in this case, if you see, both of these heuristics are consistent. So they are, so you know that already a consistent heuristic is always admissible. So it means that they both of them are admissible also, because they are already consistent. So yeah, so here is another example for 8 puzzle problem. So we have discussed what you call contour state space, or IDA star, where what we have discussed, that uh, there will be a cutoff value. So based on that cutoff value, only the states whose heuristic value is less than cutoff value, only that states will be explored, or whose evaluation function is less than the cutoff value, less than or equal to cutoff value, only those states will be explored. Other states will not be explored. And later in the next round, the cutoff will be increased. So here is an example for that. Here there is how we got this value 4. Here we are assuming that f of n is equal to h of n. That is, f of n is same as the heuristic function. So we got 4 because we are following the first heuristic function, which states that how many misplaced tiles. So this yellow color tile, is it misplaced? Yes, it is misplaced. Is this brown color tile, is it misplaced? So this is the initial state, and this is the goal state. Compare these two. Is this brown color is misplaced? Yes. Is this red is misplaced? No. Is this green is this light green is misplaced? Yes. Okay. Is this what you call, this is misplaced? Blue? Yes. Is this rose is misplaced? No. Is the orange is misplaced? No. Is the green is misplaced? No. This is an empty location. Okay. So how many tiles were misplaced? 4. So that is how we got this 4. Right. Now this is one possible move. This, when this yellow is moved here, when this yellow is moved here, now the h of n or f of n value becomes 6. But this we cannot include because our cutoff is 4. So we won't include this, so that we are showing like this. And this is another possible move. You can just move this blue here down. Now it remains in, now it remains in 4, its heuristic value. And this is another case where this what do you call, how we got this, from this state we got this, that is, uh, this rose is moved here, so then it becomes 6, but we cannot include this. This is another state. Here uh, here this brown is moved down, but again its cost is 5, so we cannot include this, heuristic cost is 5. So this is another state where what you call, this some tile is moved. Which tile is moved? The yeah. So basically, so the previously white was here, now white is here. So uh, so from here we have reached to this state. So the light green is moved here, right? But still the cost is 5, so we cannot include this. And this is another possibility, from this state to this, that is, we have moved the green here, but still its cost is 5. So basically we tried exploring several states, but we are unable to reach, unable to find a cutoff of less than 4. So we are increasing the cutoff. So now when you increase the cutoff, we are getting like this. You're getting. So when now also we can include only with cutoff 5. Now our cutoff is 5. So with cutoff 5, we are reaching the goal state, right? So this is something. This is an optimal solution. Okay, so coming to the point of today's discussion. So next, what we are going to, uh, yeah. Uh, we yeah. So we have discussed that there are two heuristics. There are two heuristics. Hmm. One with what you call H1 and H2 for solving the puzzle problem, 8 puzzle problem. Now let us try to understand like which heuristic is better than the other. So in this particular this table, what it shows means uh, to test the heuristic function of H1 and H2, we have generated 1200 random problems. 1200 random problems were generated, where each random problem is of length from 2 to 24. So that means the depth. That means at which level the solution is available. So the depth, if the solution is available at depth 2, then so that is this case. At depth 4, depth 6, only even numbers were considered, 2 to 24. And for depth 2, 100 problems were created. For depth 4, 100 problems were generated. For depth 6, 100 problems were generated. So totally there are 12 values. For each of the 1200 problems were generated. So 2200 problems. Are you getting? And then the average of its performance were taken. And then the average of its performance were taken. So that is what this table shows. Okay. So so there were 100 problems with the depth 2, with depth 2. When those 100 problems were solved using IDS, so this is a uninformed search technique. This is uninformed iterative deepening depth first search. When it is solved using IDS, the solution will be the solution to reach the solution, it has generated 10 nodes. But when it is solved using, so this is average, averagely it generated 10 nodes, because here how many at depth 2 we have how many problems? 100 problems. So some problem might have reached solution at at 8 steps at the depth of 8. Some problem might have reached solution at the depth of 12, some 10, some 9, so on and so forth, all the 100. When you take an average of that, how many nodes it has generated. Sorry, this is number of nodes. Some nodes, so at depth 200 problems were generated. First problem, say it has generated 8 nodes to reach the goal state. Second problem, 12 nodes. Third problem, 10 nodes. Fourth problem, 9 nodes. So these are nodes generated. So then all the 100 problems, each of the 100 problem, how many nodes they generated, take the average of that. So we got this 10. Is that clear? So that is with IDS. But when you solve the same problem, all those 100 problems with where the solution is available at the depth of 2, when you use A-star algorithm with the H1 heuristic. So all this we are discussing for the 8 puzzle problem using the first heuristic, that is the how many tiles were misplaced. And then it generates only six nodes. Okay, so in that case each tile position is one node. Okay, it generates only 6 nodes or 6 states. When you use A-star algorithm with second heuristic function, it also created 6 nodes only. Okay, so but you see these ideas, as the depth increases, when the depth becomes 4, 6, 8, 10, when the depth becomes 12, it is generating this many nodes. And then its memory requirement will increase exponentially. Beyond this, we are unable to use ADS. Beyond this, they are unable to use IDS, iterative deepening depth first search, because it is generating more nodes. It is going beyond the memory requirement. But when you see Yester algorithm, it is with H1, it is gradually increasing. Uh, so so with when when the solution is available at depth 4, it has generated 13 nodes. But with heuristic function H2, it generated only 12 nodes. When the average number of nodes, when the solution is at depth 6, the average number of nodes generated for H1 heuristic is 20, whereas for H2 heuristic is 18. It's only 18. Okay. Similarly, for depth 8, For H1 it is 39, for H2 it is 25. For depth 10, H1 it is 93, the average number of nodes generated for all the 100 problems. Okay, for each depth we have 100 problems, whereas for with H2 it's only the average number of nodes generated is only 39. So the point is actually H2 is performing better than H1. You can see here when the depth is 24, the and for for the for the depth of 24 also there are 100 problems, and the average number of nodes generated with H1 is 39,135 nodes, whereas with H2 is it's only 1641 nodes, right? So the point we are discussing here is actually in this case the heuristic H2 performs better than H1. So the heuristic plays a crucial role in determining the effectiveness of the algorithm. Even though both the heuristics were consistent, both the heuristic were consistent. That is, as they are consistent, they are also admissible. But even then, one heuristic is better than the other heuristic, right? So that's the key point. And one more thing which we'll be discussing is so the effect of a heuristic accuracy on performance. So how good the heuristic is, to that extent your performance will increase. The algorithm's performance will increase, right? So this can be somehow determined by a factor called as by a this can be somehow calculated by something called as effective branch factor. So how do we know whether our heuristic is good or not? So this can be determined by something called as effective branch factor. So what is an effective branch factor? That's what we are going to discuss. Okay. So for example, assume that A star algorithm finds a solution at depth 5. A star algorithm for a given problem finds us, it can be anything, it can be 8 puzzle or whatever it may be. It finds the solution at depth 5 and it has generated 52 nodes. And it has generated 52 nodes. Then its effective branch factor is 1.92. Then its effective branch factor is 1.92. So why it is 1.92, you may ask. So how we got this value 1.92 means it's depth 5. Depth 5 means, so what we are saying, that is root node we are considering 0. So one apart from root node, so root node we are assuming as 0. So 1, 2, 3, 4, 5. Okay. So basically it is 6. So how to calculate the branch factor means how many nodes the algorithm is having, that is n nodes, n to the power of n to the power of 1 by d, where d is the depth. This will give the branching factor. This will give the effective branching factor, not branching factor. Branching factor is number of children a node can have, maximum number of children a node can have. Whereas effective branching factor is calculated like this: n, that is total number of nodes generated to the power of 1 by d. Okay. So let us calculate that. So in our case, it is what is that? So d is 6, right? So depth is 5, but including root it becomes 6. So 1 by 6 is 0.167. 0.167, and n is what? 52. 52 to the power of 0.167. Right? So 1.93 something. So I think there we got 1.92. It's close to that. So that is how we got this branching factor. And study says that a well-designed heuristic would have an effective branching factor. It's effective branching factor. Sorry, sometimes I'm saying is branching factor. So the research says that a well-designed heuristic function would have an effective branch factor close to 1. Okay. So if the effective branch factor is close to 1, so close to 1 is something less than 2 is also fine. Then it is fairly it is a good heuristic function. So if the effective branch factor is close to 1, then it allows fairly large problems to be solved at a reasonable computational cost. So that is the key. So if the effective heuristic branch factor is around 1, then even large problems can be solved at less computational cost. Okay. Sorry. So this is general equation to calculate the number of nodes, right? Number of nodes is equal to 1 plus b star. So here b star represents, b represents branching factor, here b star represents effective branching factor. So now coming to this table again. So this table, what it shows, actually it shows the effective branching factor. So for IDS, the effective branching factor, if you see, it is all more than 2.45. So effective branching factor can be calculated for any algorithm. It is just number of nodes generated to the power of 1 by d at what depth. Okay. So here it is 10. So it is I mean the number of nodes generated is 10 and the d is 2. So it is 10 to the power 1 by 3, right? Whereas in this case it is 6. So it is I mean number of node generated is 6. So it is 6 to the power 1 by 3. So this is also 6 to the power 1 by 3. So like that, when you calculate the effective branching factor for this H1 and H2, you see it is around 1. It always stays around 1, so that it is able to solve the uh, heavy large problems also. It is able to solve large problems with less computational cost. Okay, fine. So let us stop here for today's discussion. Yes, yes, thank you.